Welcome, folks, to our Lunch and Learn today about HyBrTec, a patented process for turning wet wastewater sludge into hydrogen gas and heat. This is our first installment for 2022, and everyone should be muted as you join the webinar. And please just stay on mute until we get to the end when I can open it up for questions and let you speak. You can also use the Q&A function at the bottom of your screen to put questions in while you think of it. The session is being recorded, and the link to the recording will be shared with everyone who registered after the fact, and will also be available on demand to NEBRA members who were not able to make it today. So thank you for joining us, and I'm very excited to talk about a new technology for managing biosolids. This webinar is sort of a spin-off from our residuals conference in October, when we did have like 20 minutes to talk about this, but we're going to expand it a little bit, and the project's actually advanced since then. So we'll be able to really dig into this technology. And I'm so pleased to have Dr. Milan Parker here with us today, principal at Chemergy, which is a startup with innovative ideas and potentially commercially viable, sustainable technology for dealing with our wastewater solids. You can see his resume up there. He has 5 degrees. I think he was trying to decide between chemical engineering and aerospace engineering. But finally, the PhD came in 2009 from Stanford University. And so he's done a lot of research. He's been responsible for research for major companies like Sandia National Laboratory, Northrop Grumman Corporation, and Boeing. So he has a lot of experience. We're very excited to hear about this technology, and I will let you take it away from me.
Hey, thank you very much. One thing is that I very much hope this can be a conversation. So I'll go through and present what we're working on. But I do hope that we can have some dialogue. I don't see any other members in the screen.
Milan, so let me just say, folks, if you want to raise your hand, that is a function at the bottom. I will see that, and if you don't mind, we'll stop and ask the questions as they come up. It's fine with me.
Great, because I live and breathe this I've lived and breathed it for years, and so I might gloss over things that you might want more information on. But I think one thing about my bio is that I focused on aerospace engineering as an undergrad and then in grad school. And then as the energy crisis unfolded in the noughts, I shifted towards energy. And that's what puts me here now with Chemergy, working on waste to energy. So to start things off, okay, so basically, HyBrTec, that's our patented technology. Simply put, it converts wet organic or plastic waste into hydrogen. It reduces that waste significantly. So we're basically only left with the inorganics, which in the case of biosolids is 3 to 5% of the total mass of the input biosolids. An important part is that we're using less than half the electricity of water electrolysis. And we're now fabricating a pilot for demonstration at Miami-Dade Water and Sewer Department. So why we're here, also just to reiterate that, so I'm really here to try to network with other people who are involved in biosolids, to get closer to our potential customers. It would be fantastic if we could identify some funding to help support the work. I can go into that further, but we're basically a startup where we're very capitally constrained, which means that we're moving a lot slower than I'd like for us to be moving. It'd be great to identify a host site. Like we have a host site with Miami-Dade, but ideally in line with some funding, we could do a demonstration at your host site, to show this and to further support the R&D and the eventual commercialization. And then also, if there's other technology providers that might be able to assist us in that commercialization, then I'm welcome to those conversations too. Chemergy, right now, Chemergy is a 5-person operation with a small lab and we mostly contract. We're contracting to have the pilot built now. So we're a little tiny company with a very big idea. So the problems that we're addressing, the first is regards to the waste. So we take a waste and we're able to effectively eliminate that. The second problem relates to producing green hydrogen. And so in the process of getting rid of that waste, we can make hydrogen at significantly less energy requirement of water electrolysis, which creates an opportunity to decarbonize industry and some of the transport. Getting to the juice of the process, our process works in two major steps. So in the first step, we're reacting the wet biosolids with bromine so that the carbon and the water in the biosolids reacts with bromine. The CO2 is formed. So immediately the carbon's going to CO2, like with a very short reaction time. And the hydrobromic acid is produced. We take that hydrobromic acid and we electrolyze it. So we're putting electricity in, which allows us to produce net hydrogen and regenerate the bromine. And then the remaining inorganics are removed from the first step as in the ash residue. So this is mostly sand, but also includes all the metals that are present. Basically any inorganics would be in that. And I think that if you think of our technology in comparison to alternatives of, if you consider anaerobic digestion, like bugs on one side, and then gasification on the other side in terms of temperature, like gasification is very fast, it's very hot also. The bugs are very slow and they don't react all the waste. They leave a lot of carbon behind. And one of the innovations in our process is that we do release a lot of heat in the bromination. So we're getting about half of the heat that you would get if you burn with oxygen by burning with bromine. Bromines and oxidizer similar to oxygen. And so that heat is available for some beneficial use. But an important part of this process is that we're actually operating at quite low temperatures, less than 300 Celsius, which, and the reason we're able to do that is because we're using electricity to regenerate the bromine. So we're using the benefits of electricity to circumvent the high temperature steps normally involved in such waste reduction technologies. So regarding just to reiterate the steps. So the first step, we do the bromination. We basically oxidize the reactants. We oxidize the carbon with water and bromine to produce hydrobromic acid. And the electrolysis, we electrolyze the hydrobromic acid to make hydrogen and bromine. An important feature of this is that because we're brominating the waste, we're breaking down all of the complex molecules. So the pharmaceuticals, any pathogens, vectors, organic chemicals get broken down. The metals get concentrated. So we have a process to recover the bromine, because the bromine forms metal bromides, which we then recover. And so the ash doesn't have bromide in it. And then, so that remaining ash is actually sterile and it can be safely disposed or recycled depending on what's in it. And so another thing is that we work at relatively small scale. Like we always have better economics at larger scale, but we can be at relatively small scale in the sense of we can handle our smallest system is designed for 10 tons of biosolids a day. And so there's something that where this could be a community level solution. If you look at the wastewater treatment plants, many plants are much less than 10 tons a day. In those cases, those might be community plants that also collect the municipal solid waste, that also connect the yard waste, agricultural residues, animal manure, etc. And so that's something else about this process. Like we're focused on biosolids initially because they have a very high pain point with the disposal. But we're also applicable to other wet organic and plastic waste streams. So the key advantage is, again, we sterilize that waste. We significantly reduce the mass of it. We use water as a co-reactant. And so we're actually using 58% water as a co-reactant to the process, which reduces the need to dry it. The waste heat that we have is able to get it from 75 weight percent water to the 50%. So that's one of the uses of our waste heat. So we can come out of a centrifuge or a belt press. Another big fundamental advantage is that we're electrolyzing hydrobromic acid, which is much easier to electrolyze than water. So when people discuss how we're going to decarbonize energy in the future, hydrogen is one of the solutions. It's not going to meet all of energy demand clearly, but there are specific niches where it's very important, where it's the best option. And the main way that it's being done now is through water electrolysis. We can effectively make twice as much hydrogen from the same electric resource. And this is something that's important now because renewable electricity is very affordable. In the last 10 years, there's been a significant drop in renewable electricity generation costs. And renewable electricity is the generation that's being installed now. So there's no more argument over you're using fossil energy to make electricity to make hydrogen. The marginal production, new production, it's renewables. And something that I haven't discussed yet, but it's important for the long-term viability of this, is that the hydrogen bromine couple is very reversible. It's a very efficient. It's an ionic bond, and it's in a very conductive solution. And it's very easy to both separate the hydrogen in the bromine from hydrobromic acid to produce hydrogen and bromine. And it's also easy to combine hydrogen and bromine to make hydrobromic acid and electricity. And so the same system that electrolyzes the hydrobromic acid to regenerate the bromine can also take bromine and hydrogen into it. If instead of having an electrolyzer, we have a reversible fuel cell, or regenerative fuel cell, then our system can function as a flow battery. And this is important for several reasons. So one is you are able to operate the asset 24 hours a day based on the power prices. So if power prices get expensive, you wouldn't want to make hydrogen during those times. Well, now you not only don't have to make hydrogen, you can actually discharge electricity. So you can do load leveling and energy arbitrage. What's perhaps more important for a critical infrastructure such as a wastewater treatment plant is that you can meet your backup power requirements. And so you're potentially retiring your diesel gen sets and using the flow battery instead. And this feeds into a vision for a wastewater treatment plant of the future where you're converting you're no longer trucking waste away. You're converting it on site into hydrogen. The hydrogen can be used in your biogas generators, or it can be more preferably used in transport to fuel fleet vehicles or buses. And meanwhile, the system is also doing energy storage so that you can expand your solar and wind resources possibly on site or in the local community. And this can be, the wastewater treatment plant can become part of improving the resiliency of the electric grid. So there's a lot of opportunity with this technology. So just a simple thing on the mass balance. If you have a ton of wet biosolids coming in as received, we remove some of that water initially, and that can be done with the waste heat from the process. Then we do the reaction, and so effectively all that carbon is going to CO2. And on initial review, people are generally concerned that we're producing CO2. But I think it's important to note that this CO2 is coming from biosolids. It's from a biomass resource. So this is actually technically green CO2. And when you run the numbers on the carbon balance, we're actually carbon negative. So if you make hydrogen from steam methane reforming, so just making it from methane, you produce about 9 kilograms of CO2 per kilogram of hydrogen. In our process, you're -3 kilograms of CO2 per kilogram of hydrogen. And that's because you have avoided emissions from truck transport of the biosolids to a landfill, to an agricultural land for land spreading. You also have avoided emissions from methane and nitrous oxides, which do not form because we take that carbon right to CO2 instead of leaving it in a field where it eventually decays into CO2, but also produces methane and nitrous oxides. So this slide shows the energy requirement of water electrolysis compared to hydrobromic acid electrolysis. And you can see the blue bar represents the theoretical and the red is the actual. And that's because you have internal losses, you have activation losses to do the electrolysis. Water electrolysis is a 3-body reaction versus the HBr electrolysis, which is 2-body. And so it's much easier to do the HBr electrolysis effectively. And you see on the right, there's an example of the actual kilowatt hours per pound of hydrogen. And this is just to show how much less we can be than other commercial systems. So we're looking at less than half the energy requirement of water electrolysis. The point I made about the energy storage, it's just to show like our system can function as a battery when desired. And that's better illustrated. And the reason for that is because of the very efficient HBr couple, which I can discuss more later. But this is an illustration of how a system could work. So you have, and it gets a bit complicated here. So you can imagine there's that first step that's reacting the waste is happening all the time, 24 hours a day. You're taking in waste and you're converting it to HBr. You then have buffer tanks where you store that product solution. And based on the market conditions mainly, or if there's a power outage, for instance, when prices for electricity are high or there's a power outage, you can take in some of the hydrogen and bromine and make electricity. And that's shown on the right side. During low price periods, or when electricity is widely available, you can take electricity in and produce net hydrogen and regenerate the bromine. And that's shown on the left side. And so then the traction we have at the moment is that, so Miami-Dade is hosting a demo for us. So currently Miami-Dade ships their biosolids to Central Florida, where they contribute to nutrient overload, which contributes to algae blooms and other problems which hurt Florida's hospitality industry. So as a result of that, the Florida Department of Environmental Protection is funding us to do a pilot demonstration at Miami-Dade Water and Sewer Department. We're currently engineering that pilot. We've started fabricating components of it. We plan to have it operational in July of this year at Miami-Dade. And this is a small pilot, to be clear. It's small relative to commercial plants. Like we're looking at, we have a 5-gallon reactor, for instance, with a 5-kilowatt electrolyzer. So very far from economical, but that's much, much larger than what we were doing in the lab before. And so about where we are in the roadmap. So we've demonstrated that everything works in the lab. We know the science is there. We've produced hydrobromic acid from biosolids. We've electrolyzed hydrobromic acid to make hydrogen and bromine. What we're now doing is we're addressing the engineering risk in this first pilot. The main point is to provide a robust test bed, which will allow us to evaluate the reactions at a wider range of conditions, and more importantly, to operate everything continuously. So the feedstock will continuously come in and hydrogen will continuously go out, and ash will continuously come out. And so we'll be able to validate the controls that we have and all of the process steps, which then allow us to scale up in a second pilot where we validate the economics. And so in the second pilot, we use larger equipment, which then allows us to have some economies of scale, which and higher throughputs, which means that instead of just venting the hydrogen, we'll start to put it to beneficial use. And this is where we plan to validate the cost, which would then justify the commercialization. Something about the market. So we're focused on the biosolids from wastewater treatment plants now, but the process is applicable to any wet organic or a plastic waste. And so we see ourselves moving into municipal solid waste, so that this test bed that we're building now, we hope to use it to evaluate municipal solid waste in a follow-on program. And then we would move into animal manure, agricultural residues. It's really based on the revenue that we can get in the tipping fee. We're trying to validate it on the most expensive waste to start. To give an order of magnitude of what we can do, there's something like I understand there's 80 million wet tons of biosolids produced in the US a year. And that number really surprised me, except for when you factor in that it's wet. So most of that's water. There's another 200 million tons of municipal solid waste. But if you factor in animal manure, agricultural residues, forest residues, there's 1 billion tons of waste available in the US. And if we can convert all of that to hydrogen using our process, we're looking at replacing 50% of the crude oil, meeting 50% of the 55% of the crude oil consumption in the US. And so this doesn't solve everything, but it solves a significant piece. And of course, we're not going to capture all of that waste, but the point is that this can be a significant source of hydrogen for the future. So I think that's it for my core presentation. I think based on questions, I can present some more slides. I think it's just one point about this process is that when we run the numbers for it, we have we get about we get 40% of our revenue from biosolid tipping fees, and then 60% of our revenue from actual hydrogen sales at $3 a kilogram. And then our main costs are electricity, and then there's operational and maintenance costs and paying back the CapEx. But we anticipate having a 30% return on investment for our beta system, which is a 40-ton-a-day system. And another order of magnitude, if we were to adopt our system at all the US wastewater treatment plants, we expect that would require an $8 billion investment, and which would then generate $2 billion in pre-tax revenue a year. So our ambition here is validate the technology and then start to install it at plants. We're not looking for wastewater treatment plants to buy our technology. We very much like to have a service model. So we would like to build, own, and operate our systems, and just it'd be as simple as you deliver us your biosolids, pay us to take it, ideally, and then we'll handle the offtakes of hydrogen. We just like to have a piece of land next to you to put our plant. And so with that, thank you very much for your time.
Oh, great. Thank you so much, Milan. Let's see if we have any questions, but I wanted to start on the economics. What do you, I know you're not at full scale of economies or anything like that, but up here in the Northeast, we're probably looking at $130, $140 per wet ton to dispose of solids. Are you anywhere close to that? Or do you
My
see
assumptions are that we receive $50 a ton for the biosolids.
Okay.
So yeah, but another thing is, like, we look at the market and we use averages, but there's really, like, the fact that you're paying 130, 140 means that we would very much like to install a plant there, and ideally we would be able to charge you like $90 or $100 a ton, you know, something that is a win-win for everyone. The wastewater treatment plant only needs to approve an OPEX budget for that. That OPEX budget is less than what they're expecting to pay anyway. And then that effectively subsidizes our early systems, which will cost a lot more. You know, our first systems aren't going to be profitable, but we need to build them to get to the profitable systems.
Yeah. you're a better man than I am. Yeah, that's a tough field to be in, but this is pretty exciting. Let's see what we have for questions here for you. Carol's asking if are there solids produced from the process? I believe yes. How much compared to anaerobic digestion, for example?
So this is a great question because it allows me to say that we're taking the digestate from the anaerobic digester. And so the way we plan to take biosolids, it's already been anaerobic digested. And we're taking all of that and then we're reducing it to the inorganic fraction. So if you have, most of the inorganics tend to be sand. And so you can generally use that. It's like we reduce the waste down to 3 to 5% of its initial mass, typically. But it's important because we can potentially take raw sewage in our process. So there's nothing like we're not looking to displace anaerobic digesters or to have you not, to disassemble your AED system. That you've invested in that, that's working, that's very nice. But we can potentially take raw waste into the process also. And then we would have higher yields. We're getting 100 kilograms per ton of biosolids, of dry biosolids. When we start to use the raw feedstock, that goes up to 150, even 180 kilograms per ton. And that's largely because there's a much higher carbon and hydrogen ratio in the feedstock, whereas the biosolids has a higher oxygen ratio.
All right, there's some good questions in here in both the chat and the QA, so let's keep going here. One of our Canadian members is asking, could you treat drier biomass like contaminated wood from construction and demolition sector? And in Canada, big on recycling ashes over there. Can you recycle that ash that you're generating, or is it too contaminated?
Yes, so the ash is completely dependent on that initial feedstock. So if you have mercury and lead and cadmium and whatever other metals in the source material, then you don't want to put that on agricultural land. Like you're like an advantage here is that that much smaller amount can then be properly landfilled, or we're looking at it can be used as an aggregate in cement, for instance. So but it all depends on that initial feedstock. If there's waste in that feedstock, you want to lock the remaining ash into something that keeps it out of the biosphere. If you're using animal manure, for instance, then absolutely that becomes a soil amendment, a micronutrient fertilizer that you would then want to put back into the land. The construction waste, so we want to avoid inorganic fractions. So like municipal solid waste is a good example because we don't want to put glass through the process. We don't want to put metal through the process. We want to separate that and only use the organics. Now, wood construction waste, like I anticipate there's no reason we can't take the sand and the grit through our process. Like it'll just pass through the system, but it would cause higher maintenance burden on the system. And so our preference would be to have some separation to at least remove the majority of the rocks.
Okay, and we know this is all evolving, but all right, another question is, how do you compare with sludge incineration at 30% solid content in terms of energy production and costs?
Okay, so I don't have the exact numbers in front of me on the sludge incineration. I think that my basic understanding is that with sludge incineration, you're using a lot of natural gas or coal in order to account for the water content, to accommodate the water content. And then you're relying on air emission controls to capture all the waste products. I'm not very confident in all those air emission controls personally. I am much happier with with having those emissions stay in an aqueous solution that then gets removed. Those emissions don't get hot enough to boil off to get in the air in the first place. And regarding economics, I don't have that comparison now. I mean, there's so much variability in waste incineration. I just don't know. I mean, I know that based on our forecast for our costs, we're very competitive. And that's just based on being able to sell hydrogen at $3 a kilogram, which is effectively half the price of diesel or gasoline on an energy basis. And I mean, the other thing is, like, long term, I expect us to be able to get to $2 a kilogram for hydrogen and potentially $1 a kilogram. And that's really driven by, so I didn't mention this, but I've promoted this this first iteration of the technology. And there's a second and a third iteration of the technology, which becomes even more efficient. And what happens is that the HBr electrolysis is strongly dependent on temperature. And so by being able to, at room temperature, we're easily electrolyzing below 1 volt. By going to higher temperatures, we can get down to 0.6 volts, 0.5 volts. And so you actually see, when electricity becomes your biggest input cost, we're able to significantly reduce that over the alternative.
Well, the potential is very exciting here. Very good practical question from our members out in New York. Have you identified any special permitting requirements for the process, especially air or related to hydrogen?
Yes. So the main it helps also that we're starting with wastewater treatment plants, because the main permitting requirements relate to the presence of hydrobromic acid and bromine. And it's useful because wastewater treatment plants are familiar with chlorine and hypochlorite. And so they're similar handling characteristics as our solution. Another thing is, we're never dealing with liquid bromine, so which does require extra caution. We always have aqueous solutions of bromine in hydrobromic acid. And so it has much lower vapor pressure and much less corrosivity. So those are the hydrogen. I don't think hydrogen is a particular problem. Like, there's been a lot of work done on permitting hydrogen. I think the biggest concern is simply comes down to the hydrobromic acid.
As expected. So I have another question too about energy storage. So, and that's awesome that you factor this into the process, because that's one of the big issues with renewables. So how did that fit in the process? How did you come up with that? And yeah, what does that involve?
Okay, so hydrogen bromine energy storage was first developed in the 70s.
Really?
Yep. It was actually developed as a way to isolate our nuclear missiles from the electric grid in case of a nuclear war. So that they would have HBr batteries to serve as their backup power supply. It was also investigated before hydrogen oxygen fuel cells because the kinetics were much more favorable. And so a lot of the technology, as they were developing hydrogen oxygen fuel cells for the space program, they were also looking at hydrogen halogen electrolysis for backup power, for energy storage, effectively. There's a company working on HBr energy storage currently in the Netherlands. They're in the process of commercializing a product. The way that fits in is it means that once they commercialize their product, it becomes a commercial off-the-shelf piece of equipment that we can buy and put in our system. We don't have to develop energy storage for our process to work. The number one benefit is the waste reduction. The second one is the hydrogen production. That third one is the energy storage. But we have worked in energy storage. We do have reversible stacks. And so it is something we can look at, but it requires investment to develop it at this point.
I see.
I think this also relates to the long-term potential of the technology, where the market might not support energy storage. It supports it in specific instances, but longer term, you can expect energy storage to be more supported. And so you can imagine our system. So for instance, the beta system, we anticipate a price of $4 million for that system. There'll be a point where if you want energy storage, you can make the decision, is it worth the extra $500,000 to have energy storage in that system? And based on your circumstances, it might be added, it might not be added.
So yeah, that's farther along than I thought, and that was a good way. That's a good way to approach it, I think. I could definitely see that being useful at a treatment facility. All right, I can certainly unmute folks if you want. If anyone wants to, I think I can unmute. Let me just see if there's any more questions quickly.
And I think one thing out of this call, it would be really useful for me if any of you wanted to follow up with a conversation afterwards to help me understand, like, what is your biosolid disposal cost? You know, how much of that is transport versus tipping fee? Like, what are your diesel genset costs? You know, is it actually a big expense to maintain your diesel gensets? You know, how valuable is energy storage? You know, are you looking at installing solar? Are you looking at using hydrogen? You know, like just to have a conversation with those of you who are actually working in this field, it helps me strengthen my message. And then ideally from that, maybe there's a letter that says, hey, if we build it, you would like to operate it. You know, you would like us to install it, because that goes a long way when I'm raising private funds from investors. You know, like I'm reaching out to VCs to support the development. And if they know that there's customers that are actually wanting this, then that helps me a lot.
Well, we'll certainly see how we can help you with that. There were a couple more good questions in here. So how long can you recycle the bromine is a good question.
So we have 99.99% recovery in the lab. That is sufficient for the process. But this pilot that we're building now is really going to validate that at a higher throughput.
Yep.
You know, because we're going from reacting like hundreds of grams of feedstock to operating 100 kilograms per day of feedstock. Yeah. So it's a significant jump that we're doing now. And the bromine, so we're never going to get all the bromine, but as long as we're below 99%, then it doesn't hurt the the economics are fine.
And then there was another question again on the ash or solid output. Is it, if it's just inorganic? Yeah, I guess you said it already. It depends on what's in it, but is that something that can add to soil health?
Yeah, yep. All
it depends.
In there. I mean, I think a big problem now is the first time you add biosolids to land, it's not a big deal because it's, you know, dilution's the solution for pollution. But the 100th time or the 200th time you add it, you start to accumulate quite a lot of these toxins, and it starts to become really noticeable in the feed that shows up in the crops, all that. So it's like we're trying to make it unnecessary to dispose of the waste on land, because the quantity becomes so small that it's fine to put it in a landfill or to put into concrete as an aggregate.
We need all the options we can get here. The biosolids management's on a shaky three-legged stool right now. So a fourth leg, something like this is certainly welcomed, and we'll scrutinize it, but we will help you if we can. I
think I haven't mentioned the PFAs, which I understand is
okay. PFAS was going to be a question. Yeah,
and I think so we haven't operated at large enough volumes to validate that they are destroyed, but all of our understanding, we anticipate destroying those in our first step. So we effectively, the carbon in the PFAS goes to CO2, and then you're left over with fluorides and chlorides that remain in the ash. So we anticipate this being a total solution for PFAS.
And so you're planning to analyze that at some point when you get up to scale.
Yes, in the current pilot will be doing that.
All right. Again, we are all rooting for you. Hold on. Does anyone else have any questions? I have a little poll here I'll put up if you guys have a second. Just to help, if there is anyone interested that's in the group, I'll put this out there so I can maybe connect you all. And then we got another comment in chat here while we're waiting. All right, well, I'll take a look at that after. All right, in the chat again now, phosphorus recovery extraction could be an option for, yep, we could take that out like we do with struvite or something like that. All right, well, if there are no other questions, I want to thank everyone for joining us again today. I'm going to follow up with an email to all of you, and yeah, you can just let me know if you're interested in connecting and learning more about this technology, especially as it's starting to kick off down there in Miami-Dade, where biosolids are not causing the algae blooms. It's bad management practices.
Wait, the biosolids are just contributing to the algae blooms because it also comes from the agricultural industry. There's a lot of sources for the nutrients.
Yes. Yep.
The one thing I didn't mention is that I have some good news in terms of our next steps. We've been awarded a place in the Halliburton Lab Scalerator, and so we're in the process of onboarding them, but they'll effectively be a partner in getting us commercial. And so I think that's, they're a more established company that should give us more credibility with what we're doing.
Congratulations. Yeah, you have progressed a little bit since October. It hasn't been that long, but good job.
Yep.
And again, we're all rooting for you. But if there's no other, go ahead.
Yeah, just a 15-20 minute call with you about your costs and everything would be much appreciated. And I thank you for the time to present to your audience today.
You're very welcome. And thanks again to all of you for joining us today. Our next session is scheduled for February 25th, and it's all about a specialized IT system for managing residuals and making the best use of them. I'm always looking for suggestions for these lunch and learns. So if there's something you want to lunch and learn about, please let me know. And I look forward to seeing you next month. Thank you again so much, Dr. Parker, and everyone have a terrific weekend.
Thank you.